We are now going to start a unit on two-dimensional motion, and that includes circular and parabolic. So first we're going to analyze circular motion, and first consider an object moving around in a circle. I usually put an object on a string and twirl it overhead, so you can think of that. Maybe this is looking from the top, looking down on it, and the object is moving around the circle. So we're going to consider that that R is the designation for the position vector. It's where the object is. So there's R1, and there's R2, and there's R3, and on it goes, R4, etc., etc. And as the object goes around the circle, we can specify its position with any one of these R's, these vectors corresponding to the position. It starts in the center, and its position is right here in the case of R1, R2, R3, etc. As you saw those vectors being added, what was the object doing? It was rotating around the circle. Alright, so that's pretty obvious, but you're not really used to thinking of its position as being a vector position with the reference frame being at the center and moving out to the edge of the circle. So this represents that position. Okay. Now we have a displacement. When we go from R1 to R2, the difference between those is this. We start here and we end here. The displacement is from beginning to end. R1 plus the displacement gets you to R2, the final position. Initial plus displacement is final. Moreover, what about the motion? We'll designate that as V. And you may realize already that if the object is right here on the edge and it's moving around the circle, then the motion right here, for instance, is this way. At that moment, it's tangent to the circle. So there it is, V1 and V2 and V3, 4, 5, 6, 7, 8, all the way around. I'm not going to put them all in there right now. Those are the velocities at any position, and notice it's always perpendicular to the radius vector. Where does R1 point? R1 is this line here. Standard north, south, east, west, it points east. What about R2? Here's R2. It's pointing mostly east, but slightly north of east. What about the displacement? Displacement isn't straight up like this, is it? It's off at a slight angle. What would we call that? Perhaps west of north? West of north. Now let's consider the entire circle again and look at the velocities and what they're doing. So we saw the position vectors rotating around the circle. Well, here's the velocity vectors. What are they doing? Let's look at it again. There's R1, and corresponding to R1 we have V1. And we have R2, and corresponding to R2 is V2. So watch as the velocity vector makes at least one revolution around here. Watch what the velocity vector is doing. I'll keep adding the position vector along with it, and you see each position vector, the corresponding velocity. What is the velocity doing? And in the same way, logically, as we answered the question in the first case with the position vector, the velocity vector is also rotating around the circle. It's changing directions in the process, just like the position vector did. So that is a brief description of what these position and velocity vectors are doing. And notice the nature of the displacement as well. It's connecting one position to the other. And now we're going to look at this a little more carefully. Well, now let's look at the velocity vectors a little more carefully. And actually what we're going to do is take those velocity vectors and move them, which we can do. We can grab the velocity vector and move them around as long as we don't change the size or direction. I'm going to move them with their tails all connected right to this point here. So there's V1, right? That was where it was going before. And now v2, and on it goes. I won't put them all here. But there's the velocity vectors with their tails connected to the center. Now it looks very analogous to the rotating position vectors, doesn't it? At this point, let's do delta v between v1 and v2. So the change going from 1 to 2 is really the difference between those vectors, v2 minus v1, which means we're going to connect the tip from there to there. So v1 plus the change is v2. There it is. So that's delta v. And what is the direction of delta v? Now, you might right away want to say, well, it's a little bit south of west. But as delta t goes to 0, in the limit as delta t goes to 0, this calculus thinking here a little bit, this gets closer, v2 gets closer and closer to v1, and so this thing, you can kind of think of this vector here, v2, as we rotate it toward v1 with a smaller delta t, it pushes up on it and makes this kind of level or horizontal. So the real answer is west. Now I'm going to bolster that momentarily with a deeper analysis of the position vectors. If that makes sense to you right now, we're good. If not, it will in a minute. So a change in velocity is taking place, right? We're going from v1 to v2. So if there's a change in velocity, the next question is, what kind of motion is the object moving in a circle experiencing? Well, anytime a change in velocity occurs, you remember from basic kinematics definitions that a change in velocity in a given amount of time, delta v over delta t, is the definition for accelerated motion. So we have acceleration. We'll come back to that. But now, let me maintain my promise to show you more detail of what's going on with the position vectors, and it will help explain this west direction of the delta v at this point. So here we have R1 and R2, and these vectors are copied. I drew them in PowerPoint, but copied one and then connected the tails together here, so they're really the exact same length. What I want to do is connect across here. Now, if I just went from here to here and stopped, that would be the displacement. But the average velocity is displacement over time. So this is really representing the average velocity over that interval. And it's longer because it's a different physical quantity. So I don't know how long it is, but it doesn't matter. It's not the displacement, it's the average velocity, which is displacement over time. All right, so now we're going to allow delta t. There's a certain delta t from R1 to R2. Let's let that t get smaller. And as delta t approaches 0, what's the direction of the displacement and therefore the direction of the average velocity? Actually, at that point, it will be the instantaneous velocity. Because when we make delta t really tiny, we're going to end up in the limit considering an instant of time. But let's go ahead and do this. So my first attempt is to split the difference here. And this is 0.5, the delta t that was represented by R2. And this is, again, the same length as these others. And notice the tip of the arrow is here. I mean, you know that this thing is going to make us a little arc as it moves across here. So here it is. And if we connect those together, R1 to R1.5, notice that it's less west and it's more north. All right, now let's do it again. Let's split the difference again. R to the R sub 1.25, or a quarter of the time. And notice again that the tip of the arrow is out here. So when we connect across from R1 to R1.25, we're getting closer and closer, as you can see, to being perpendicular to R1. Let's do it one more time. There's R to the 0.125. And actually it's R sub 1.125, right? In any case, we split the difference again, and look how that resultant the displacement, and then therefore the velocity, which is what's represented here, is pointing more and more vertical. And so the actual velocity at position 1, consistent with our intuition at the beginning of this discussion, as the delta t approaches 0, at the instant it's at R1, at that instant, it's going to point exactly straight up and down, which is north. So it's pointing due north at that moment. So there it is. Okay, hopefully that made sense. And you can see as we reduce the time, this second vector is getting closer and closer to the first one, and when it's infinitesimally close, the motion, the displacement, and therefore the average velocity, which becomes the instantaneous velocity, is perpendicular. All right, so our partial conclusion at this point is that for circular motion, velocity is perpendicular to the radius or position vector at that moment. So by analogy, the same thing will hold true for the change in the velocity vectors in the rotating vector analysis above. So we're rotating these velocity vectors, and that same thing will hold true. The change in velocity is perpendicular to the velocity at that moment.